Welcome Sahani Pathiraja, who will be telling us about new approaches to Monte Carlo based nonlinear filtering.
Thanks very much. Thanks very much to the organisers as well for the invitation to speak here. So I'm going to talk a little bit about some concepts that Alberto already raised related to data assimilation, but for a very specific problem setting. And this is joint work with Sebastian Reich from the University of Potsdam and Wilhelm Steiner from the TU Berlin. So since this is a fairly diverse audience, I'll spend a little bit more time on the background and motivation, as well as this class of what are called control type particle filters that we've been interested in looking at, before going into describing this mathematical framework that we've developed to better understand the links between these methods. And if there's enough time, I'll talk about a diffusion map-based approximation of one of these filters called the feedback particle filter. So for those of you who are familiar with data assimilation, ensemble Kalman filters in particular are prevalent in numerical weather prediction and sequential Bayesian inference or sequential filtering or sequential data assimilation. It goes by many names. Essentially, it boils down to estimating the state of some system, which we denote by X, and which evolves according to some dynamical process, which in this community is very relevant because, as Alberto mentioned, we often have good physical models. But we might also have observations of these hidden states via some indirect process, and these observations themselves might be noisy. And so what we want to be able to do is to estimate, to get a better estimate of our hidden states given our observations. And this is essentially described by Bayes' theorem. So the filtering distribution or the posterior distribution describes our uncertainty and our hidden state given our prior knowledge, which would be our model, and all of our observations up until the current time. So in the case where we have linear dynamics in our hidden state or in our system, and when the relationship between the observations and the hidden states is linear and all our distributions are Gaussian, we know that this filtering distribution or posterior distribution is going to be Gaussian as well, and the mean and covariance are given by the Kalman filter. But in the case where we have nonlinear models and our posterior distributions are non-Gaussian, we still don't have a very effective method for dealing with this situation, particularly when we have high-dimensional systems. So when this X is very high-dimensional, like we often have in numerical weather prediction. So then it's very typical to resort to Gaussian or linear type approximations, which is why the ensemble Kalman filter is so popular. So I'm going to be primarily focusing on Monte Carlo based methods for approximating this posterior distribution. So very brief recap, very standard Monte Carlo involves taking independent and identically distributed samples from your target distribution. In our case, this is our target distribution. And then we would approximate expectation functionals via sample averages of this sample. An alternative way is what's known as importance sampling. This is particularly useful when we can't actually sample from our target distribution because it might be difficult to sample from, but we can sample from some other distribution. So in the sequential filtering context, this would correspond to our posterior from the previous time propagated through our forward model. In this case, our expectational functionals would be approximated by some weighted sum, and these weights are essentially a kind of correction factor to account for the fact that we haven't sampled from our target distribution. Okay, so why am I mentioning all of this? Within Monte Carlo methods in nonlinear filtering or data assimilation, we have what's known as interacting particle methods. So interacting because the independence assumption now breaks down, because when we approximate our posterior distribution, this approximation relies on interactions between particles. They're no longer independent. So a very classical, popular zoo almost of methods are known as sequential Monte Carlo or particle filters. There's too many to name out there in terms of their variants. But they have nice theoretical properties under very mild assumptions on your system state and your observation dynamics. So meaning that they're consistent with Bayes as the number of particles tends to infinity. But they're very rarely used in practice because they're well known to suffer from the curse of dimensionality. And the reason being that they rely on the very basic forms of these methods rely on importance sampling. And these importance sampling weights, especially if they're in very low regions of probability of your posterior distribution, can end up taking very low values so that you have very few effective particles that are giving you information about the posterior distribution. So you end up needing many, many particles to effectively characterize your posterior. On the other hand, we have ensemble-Kalman type methods that Alberto mentioned. Again, there's several variants of these methods, almost too many to describe, and I've only just put the equation down for one of them. These are essentially a Monte Carlo type interpretation of a standard Kalman filter. So they're ideal because you can still make use of your nonlinear dynamics of your hidden state, but you will still rely on a kind of linear Gaussian approximation to incorporate your observations. So the consequence of that is when you have nonlinear dynamics, even if you let your number of particles tend to infinity, you won't actually generate samples from a true posterior distribution. Having said that, they tend to be very stable and provide reasonable enough estimates, especially when the number of particles is much smaller than the dimension of the state space. So this is one reason why they're so popular in numerical weather prediction, for example, when you can't afford to simulate your very expensive physical model many, many times. So one of the many reasons why ensemble-Kalman filters are thought to work well is because, unlike sequential Monte Carlo methods, they don't rely on importance weights to generate samples from your posterior, but they would rather propagate samples from your model or your prior in state space to regions of higher posterior probability. So the idea behind these types of particle filters that I'll talk about today is to kind of emulate the structure of ensemble-Kalman filters, but in such a way that you can maintain the asymptotic consistency properties of sequential Monte Carlo. So the idea being that instead of relying on a Kalman type update, we want some general control term that ensures that these samples are going to be samples from your true posterior. So if anything's unclear at any point, please just stop me. Okay, so that was kind of a high-level description of what we're looking at. Now, I'm mainly going to be focusing on continuous time in this talk. So we might have some hidden state x hat that evolves according to this Ito SDE, where dBT is a standard Wiener process. And we might have a measurement process that's also continuous in time and also noisy with a standard Wiener, given by standard Wiener noise. I'm looking at this very simple case here where the noise processes are independent and there's no time correlations. So this might not be super relevant for the kinds of models that you're considering here, but there's plenty of room for further extensions. But this is a nice starting point. As I mentioned, the goal in nonlinear filtering is to estimate this conditional distribution. So the distribution of the hidden state given this observation filtration. And I'm going to assume throughout that there are conditions on the signal and measurement process that guarantee that this distribution has a density with respect to Lebesgue. So we're just going to work with densities. And so already in around the 60s, Kushner and Stojanovich developed an SPDE. So it's not SPDE in the typical sense because it's still driven by a finite dimensional Brownian motion, but an evolution equation for this filtering density. Now, typically it's not easy to actually solve this evolution equation in very high dimensional systems. which is why we then need to resort to Monte Carlo or some other type of approximation. So a more practically relevant scenario might be when you have measurements arriving in discrete time. And the question then would be, how would we actually discretize this continuous time process? One very standard way to do that would be via an Euler-Maruyama approximation of this Ito SDE. And if you do that, you can then arrive at this very standard measurement model where you have additive Gaussian noise. And if you were to then plot this approximation in time, you would essentially end up with a piecewise constant observation trajectory. So within each interval, you would be able to propagate your signal dynamics continuously in time, but then you would essentially have a jump to account for this observation that arrives. An alternative approximation approach that has nice theoretical properties when it comes to robust filtering is what's known as a piecewise smooth approximation. So this is where, instead of considering piecewise constants, you would essentially construct something like a linear interpolation between your observations, so that at least within the interval you would have differentiability. So when you construct these control type particle filters, the overarching stochastic process that governs your filter will depend a lot on how you discretize your measurement process. So the basic idea is that each of your particles, so n being the number of particles, would evolve according to some stochastic process. And if you adopt this smooth approximation, you can essentially write down very easily or very naturally a single stochastic process that incorporates the underlying hidden dynamics plus some control term to account for your observations. Whereas if you consider an Euler-Maruyama approximation, what's typically done is to evolve the dynamics according to your signal process within each time interval, but then to write down a separate homotopy that evolves in pseudo-time lambda to incorporate your observations. So you would essentially have processes on two different timescales. So this is just to make you aware of two different approaches that have been considered in the literature. And for the rest of the talk, I'm just going to focus on the mean field limits of these equations, so not their particle versions. So here are some of the references that have considered or that have put forward methods of this type. They were all derived in very different ways. I don't have so much time to describe how exactly, but the key point being that they were derived in very different ways and also under different assumptions on the discretization of the measurement process. And this is sort of a kind of snapshot of what the different control terms or homotopies look like for these filters. The details of these terms are not super important. It's just to give you an impression of how different they all look. One thing that might be worth remembering throughout the presentation is the ensemble Kalman-Bucy filter, which takes this particular form for the control term. So this part here is known as the innovation, and this part here is your cross covariance between your hidden states and your observation space. And what's nice is that one of the filters, known as the feedback particle filter, has a very similar structure to the ensemble Kalman-Bucy filter. So this already points to some potentially nice computational advantages, since we know that this works quite well in practice. Okay, so I'll now talk about this framework that we developed to better understand these methods. So as I mentioned, they were all derived in very different ways. So it's quite difficult to see the links between all of these filters and if they were maybe just reformulations of each other. So what we wanted to do was to focus on one type of approximation. So here we considered the smooth approximation to the observations because of its importance in robust filtering. And we started off by considering this continuous discrete time case. So that was where we had a continuous signal process, but a discrete time observation model. And we then rederived the corresponding forms of some of the filters in the literature. So those are the blue ones under this assumption. And then we considered what the continuous time limit of these filters would look like. So what happens when the discretization interval, or the size of the discretization interval of the observation, when that goes to 0, what would the corresponding filters look like? So without going too much into the details, the overall idea behind the framework is actually quite simple. So we just started off with this ansatz for our stochastic process. So again, starting off with the continuous discrete time setting, so delta being the size of the discretization interval, we assume that the mean field stochastic process evolves according to equation 4. So this part here being the signal dynamics plus a control term, which we assume to take the form of some drift plus a diffusion term. The key point being that both the drift and the diffusion term depend on the law of this process. So rho t delta is the conditional density of this process given the observation filtration. And this is essentially where this interacting particle terminology comes in. So it's possible to write down the corresponding nonlinear Fokker-Planck equation for rho t delta. And since we already know that this conditional density should evolve according to the Kushner-Stratonovich equation, we end up with these nice ill-posed PDEs for these coefficients. And the fact that these PDEs are ill-posed points to the fact that there are several different ways of essentially constructing these control type particle filters, which is why you have so many of them in the literature, but it also paves the way to construct many more that might have nice computational properties.
Sorry, where does delta actually appear? I've forgotten. What's delta?
So delta was essentially the discretization interval of this measurement process. And here, since we're focusing on this piecewise smooth interpretation, we essentially assume that you have pointwise observations in time that are spaced delta apart.
Well, this is what's usually called the trapezoidal rule in deterministic problems.
Right, but you don't have.
Okay, so the z in the equation you've just shown us is
a smooth approximation.
Okay,
piecewise smooth.
Right, because the observations you assume are coming in discrete time.
No. So we assume that the underlying model is this SDE.
Sure, yes.
So it's not differentiable in time. But then we construct, because we only, that's our underlying SDE, but in practice, we might only have discrete time observations. They might be at very high frequency, but they still might be discrete. And so we want to view this as some discretization of the underlying Ito SDE. And this is one way of viewing this discretization. Okay. Yeah, so I already sort of alluded to this. So this is just to summarize what these different control terms look like under the assumptions that have been made by different researchers that have proposed these types of filters. The one thing I just wanted to point out is that, so this feedback particle filter, the drift term in this feedback particle filter looks very different to the drift term proposed by Dan Chrisan, who I think is going to be here tomorrow, in the discrete setting. So just keep that in mind for the next slide. But on top of that, an important question that we're currently very interested in is what are the computational implications of making these different choices? This is probably going to be a difficult question to answer in general. So understanding the continuous time limit is more involved mathematically. I won't go through the proof, but just present what the end result looks like, which is essentially equation 7, which is very nice because it gives a very general description of all possible filters that fall into this class. So one insight that I will mention is that, as I mentioned in the previous slide, the drift terms for the crystallization and the feedback particle filter looked very different. But when we consider the continuous time limit, under some technical conditions on the signal drift and the observation drift, what we find is that this weighted divergence-free term has to be necessarily 0. And then the only difference between the two filters is actually in this term K. So in one filter, it's of weighted gradient type, and in the other, it's just of gradient type. So the take-home message is that we actually see much stronger links between these filters that looked very different in the discrete time setting versus the continuous time setting. What you also will see is that if you make the assumption that K has a Gaussian type approximation, these Stratonovich correction terms will essentially disappear and you get back the ensemble Kalman filter. So I don't know if I have more time or if I should probably stop.
2 minutes maybe.
Okay.
We started a little late.
Okay. One of the bottlenecks of these methods is that you need to solve this PDE. You need to first make some regularizing assumption on K, and then you need to actually solve this PDE at every time. So another kind of complication in solving this PDE is that it depends on the very object that you're trying to approximate, which is this rho T, the filtering density. So the inventors of the feedback particle filter have proposed a diffusion map-based approximation. Again, I don't really have time to go through the details, but I'm very happy to chat afterwards if you're interested. And I've just written down what the form of this approximation looks like. So if you don't know diffusion maps, they're a kind of kernel-based clustering technique. So this epsilon refers to the bandwidth of your kernel. And the only thing I want to really point out is that this approximation has very much a cross-covariance type structure. And what they've shown in their paper is that for a particular choice of your kernel, when you let this bandwidth go to infinity, you actually recover the ensemble Kalman filter. So this is quite nice because it gives you a continuous bridging between a very popular approximation and an exact formulation. It's also nice in terms of computational complexity, but there's still many more questions related to accuracy, which I'll talk a bit about later. But I just wanted to kind of motivate why this might be useful when you have non-Gaussian systems. This is a very toy example from their paper where they have a posterior distribution that's bimodal, given by the dashed line. The blue is what you get from this diffusion map-based approximation, and the orange is what you get from an ensemble Kalman filter. So when you have significant deviation from Gaussianity, these methods can be really useful. I might maybe skip over this and just say that, yeah, as I mentioned, we're currently interested in accuracy. So we have some work on mean field limits, but what is maybe more interesting to this community is the accuracy of these methods and how they depend on all of these parameters that are used to construct the approximation. Yeah, so to conclude, we looked at these types of controlled type particle filters, which are potentially promising for nonlinear sequential Bayesian inference, particularly in high dimensions, as an alternative to standard sequential Monte Carlo or particle filtering. And we came up with this framework to better understand how many of these filters are related, and will also hopefully help to develop new formulations. But what we really need right now is more high dimensional empirical evidence. So if you have some applications where you think these methods might be useful, I'd be very happy to hear from you.
there any questions?
Well, I think we can chat later a bit more in detail, but I'm just curious here. First, in which way the control takes place here? So are you using the information about the data that they will come already when you're running the particle forward?
No, it's so at least in the continuous time setting, it's instantaneous. And then
And the second, you didn't mention resampling at all, or did you?
I'm sorry.
You didn't mention resampling at all.
No.
Why?
So resampling is essentially needed if you make use of importance sampling, for instance, and these techniques essentially completely sidestep importance sampling or resampling. The idea is essentially to say, let's construct a control term that gives us the distribution that we need. And there will, of course, be interactions in that control term because it depends on the conditional density of the process, but it doesn't actually rely on resampling to.
So you are not resampling at all. In the experiment, you are not resampling at all. Okay, this is very interesting. Okay.
Yeah. So I think maybe the direction you're headed in is maybe you'll need things like localization or inflation or something, some analog of that in high dimensions when you're actually applying these methods in practice. I don't really have the answer to that question, and I think it would be very interesting to see to what extent you still need to rely on these heuristics. But at least at the theoretical level, no, you don't need it.
Okay. Well, in the interest of getting some coffee, I think maybe we should postpone further questions to the discussion later on. Thank you very much.